My name is Emre Kiciman. I'm a researcher at Microsoft Research, and I'm happy to be talking to you today about some of the challenges we see in applications of causal machine learning. This is the work I'm going to discuss today is joined with many collaborators, and some of whom I've listed here on the title slide, and many others as well. Let me get started. So we're seeing today that computing is being integrated into so many parts of our society, and data-driven decision-making is really transforming how we help people through health and medicine, industry, retail, and many other domains. This integration of computing into all these domains is really being driven by the tremendous success of machine learning, and particularly of deep learning. And we see its successes everywhere in all sorts of applications, from image recognition, language translation. Really, machine learning has a great ability now to recognize patterns and generate new examples that match those patterns. Now, there are some limits, however, to how well conventional machine learning is able to support some of these applications, and that's where this story starts. So we know conventional or correlational machine learning, we know, is really all about searching through data for patterns, and the problem is that often correlational machine learning finds spurious patterns. These are patterns that seem to make sense, but are not really grounded in the underlying system. They are fragile and unstable. We see this often. We have seen this repeatedly in many applications or analyses of machine learning systems. We see that minor perturbations to stop signs, for example, cause image recognition algorithms to make incorrect predictions and misrecognize the stop sign. We see that changing the angle of digits in a digit recognition task causes accuracy to drop significantly when the model isn't prepared for it. We see that changing semantically equivalent words in a sentence can cause a question answering algorithm to make hard to understand mistakes. Now, there's one area where this sensitivity to spurious patterns causes particular problems, and that's when we are using machine learning to drive decision making. The issue here is that correlational machine learning relies on the patterns in the data it's seeing to be stable. But when we are actively changing our decision-making policy based on a machine learning model, we are actively, as a definition of the application, actively changing the patterns in the data, and thus breaking the underlying assumption of the machine learning algorithm. So here's one example. Let's say that our task is to build a decision-making support for a farmer that will tell the farmer when they should irrigate based on predicted soil moisture levels. If the soil is going to be too dry, this application will tell the farmer to irrigate. And we train these models based on years of sensor data, taking in all sorts of inputs, such as the weather, for example. And we train. Once we train these models, we start asking questions. And we say, maybe we have a question one day that says, the weather report says it's going to be very hot in a couple of days. And now the farmer asks, do I need to water my fields? This now, our machine learning model now might very well say no. The model says that based on historical data, the soil moisture is going to be very high when the temperature is high. And This is obviously, a mistake. Why is the model perhaps making this mistake? It's because in the past, historically, the farmer always watered on these extremely hot days. And that means that the soil moisture was always high when the temperature was very high. That's a pattern that's based on the farmer's past policy. And when we change that farmer's policy, we're going to break the assumptions of this model. This is an example of a spurious correlation where we have a observed data, this temperature that is causing, has an effect on soil moisture, the outcome that we care about, and on, through the farmer's policy, the farmer's action to irrigate or not. And the irrigation also now has an effect on soil moisture. The problem is that, in a sense, with a static, if we have a particular farm policy set in the system, temperature and irrigation both predict this outcome we care about, the soil moisture. The problem is underspecified because there's a, you might call it a multi-correlinearity between the temperature and the irrigation. They deter you from one, you can maybe guess the other, knowing the policy. But what if the farmer's policy changes, like we just saw? We deploy a machine learning application to drive a new policy, and that breaks this correlation. Now, if we don't know exactly how much temperature and irrigation affect the outcome we care about, we're not going to be able to then understand when we should, how we should define how much of the outcome of soil moisture is determined by irrigation, and thus when we should irrigate to compensate for changes caused by the temperature. In a sense, what we want to do is we want to disentangle the relationships we're seeing in the data that we're observing. We get to observe the joint distribution on the left. We get to sample data and observations from this system, given historical data where a particular farm policy has been observed. What we really want, though, is the joint distribution on the right, where temperature and irrigation are independent, and it's easy to read off the effect of temperature on soil moisture, the effect of irrigation on soil moisture separately. So how does causal machine learning help with this problem? And what's really the key challenge? Well, causal machine learning at its heart is about bringing in causal knowledge about the world in the form of constraints on the kinds of models we're going to apply to the data. And this knowledge can take many different forms. These constraints can come from physics, where equations describe our current understanding of physical systems. In biology and chemistry, sometimes we have knowledge of what genes or molecules are potentially related. In the context of weather simulations, for example, we might have historical models that tell us how our observations are related to each other. Regardless of where these constraints come from, they simply encode some kind of domain expertise. And these techniques then are going to be used to constrain the kinds of patterns that we're going to allow our machine learning models to learn from. Well, often one way of encoding this domain knowledge is as a causal graph that encodes the mechanisms by which a change in one variable can cause a change in another variable. And these causal graphs also, in addition to encoding mechanisms, they also encode independencies. For example, in this diagram here, we can see that A is independent of the variable C here, whereas B is caused by both C and A. Given this type of graph, we can use this now to read off conditional statistical independencies that we then enforce on our model. That is, our model is, given the constraints implied by this graph, will not pay attention to a pattern that doesn't match this graph. For example, perhaps there's some unobserved cause, like the farmer's policy, that's relating C and A to each other, and we want to explicitly tell our model not to pay attention to or leverage the patterns implied by that particular correlation, because we want it to be robust to scenarios where that correlation changes. So reasoning over the causal graph helps us identify valid estimation strategies. Valid estimation strategies for reasoning over this graph, a causal graph, helps us to identify valid strategies for taking the data we've observed from the left-hand joint distribution and creating the distribution on the right. So, for example, one way to do this is to identify all of the factors that are influencing irrigation separate from temperature and use the variance in and condition on all of the inputs to irrigation, including temperature, to directly isolate the effect of soil moisture. So in a sense here, we would be finding situations where all of the other factors that are causing soil moisture we'd be finding, the situations where all of the factors influencing soil moisture are the same except for irrigation, and then using that to calculate the effect of irrigation itself. This would be an example of a matching approach or a conditioning approach, or in Perlian language, using an adjustment formula to calculate the direct effect of irrigation on soil moisture. Other factors might identify an opportunity to use a possible instrumental variable where we find that there's some random noise that's influencing irrigation. And by following the effect of this random noise through to the correlated changes in soil moisture, we can identify the effect of irrigation on soil moisture indirectly. Now, identifying what strategy, whether it's a potential use of an adjustment formula or use of an instrumental variable approach, depends on reasoning over the correct causal graph. We have to have knowledge of that causal graph in order to know what strategy is going to be valid. This leads us to two fundamental challenges for causal inference. One is that we can't just identify that causal graph from the data alone. The problem is that multiple causal mechanisms can be fit to a single data distribution. That is, given a particular data distribution, we don't know exactly what graph might have generated that. Oftentimes, there are multiple causal graphs that could have generated the data that we observed. This means that knowledge of the specific graph has to come from outside of the data sets itself. We need to rely on some kind of human domain knowledge and assumptions. Now, this means that we are relying on that human domain knowledge and assumptions to be correct. Because we can't observe the counterfactual world, we can't make a decision, see what the outcome is, and also make the opposite decision, take a different action and see what the outcome is. This means that we can't directly calculate many of the causal effects or answers to the causal questions that we care about. We have to estimate those counterfactuals from data. This means that because we're relying on our domain knowledge and assumptions to figure out the strategy to estimate those counterfactuals, we get into this loop and a challenge in validation. How do we know that our assumptions are correct? How do we know that the final answers that we're getting that are relying on those possibly wrong assumptions are correct? If we know that our assumptions are correct, we'll be fine. But we really would like to have ways to more reliably tell. So to recap this first section of the talk, why do we want causal inference? It's because causal machine learning is going to help us apply machine learning methods to decision-making scenarios where we really want to understand the effects of decisions and actions very deeply in order to ensure that our models are robust to changes in the system, that the decision policies that we're making aren't breaking the patterns that other kinds of machine learning are depending on. This does require us to create new methods, however, to address some of the fundamental challenges here. In particular, we need to continue to find new ways of bringing in outside knowledge into this data analysis. And we have to find new ways to validate our results, or at least improve our confidence in them, because we can't use standard machine learning methods like cross-validation or relying on ground truth data. So in the rest of this talk, I want to give a little bit more insight into some of the applications, some of our experiences that are coming out of our use of causal ML in various applications. And we have two major avenues by which we are learning about the real world problems that we face when we try to use causal machine learning in practice. One avenue for learning about these problems is through our open source Python library, DoY. DoY is a library for causal machine learning that supports data scientist workflows. This is a pretty popular library, and we're seeing broad usage across multiple industries. And we're learning about some of the issues that people run into when trying to use this to model problems or decisions in the context of retail, finance scenarios, power grids, sustainability issues, and others. And of course, we're also applying causal machine learning to some of our workloads inside Microsoft and Bing Ads and Office and other places. These tend to be larger scale, more bespoke implementations of these algorithms because of the data scales involved. But we often have a little bit of an extra benefit. Sometimes we are able to run experiments to help us validate these methods. And that helps us identify and get more confidence at the kinds of methods that we can rely on to get us the right answer, and the types of signals we can use to be sure that our methods are giving us the right answers in context. So just a slide about DoY. Really, the DoY open source library that we've built is trying to help data scientists reason through some of these challenges. The problem of how we collect assumptions, turn them into a causal graph, is front and center of the process that DoY steps the data scientist through. We ensure that the data scientist has declared their assumptions as a causal graph, and then we go through the process of helping them estimate their results, and then double check those assumptions as much as possible. So we help them refute assumptions and run sensitivity analyses. And I'll say a little bit more about what we do in the library in a few slides. This is an open source community effort with over 50 contributors, and recently including Amazon and others adding significant code to this library. Right now, we're focused on expanding the library to include not just causal effect inference, but also support for additional tasks like causal discovery, robust prediction, and others. If you'd like to learn more, I would invite you to take a look at our GitHub page and the documentation we have for the library. I'm not going to say too much specifically about what we do in Bing Ads and other Microsoft applications in this presentation, but we have published several papers about our work in these domains, and you can look up these papers to learn more about some of what we've done there. But from these avenues, we research these methods, we apply them to problems inside and outside of Microsoft, and then we learn from the challenges that we see and bring those back in to motivate our next kind of research efforts. And some of the major challenges that we see in these applications is that first, we have to find new approaches to validating our causal results. I already mentioned this earlier, but the answers to these kind of what if causal questions are not observable. We don't have ground truth labels that tell us what the effect is of one of our decisions. We only know what the outcome is. We don't know the difference in outcomes, the difference that, what would have happened if we had taken the other action. And because we don't have a ground truth label on the effect that we're trying to estimate, we can't rely on cross-validation. And because data-driven cross-validation doesn't work, that means that many of our approaches to optimizing hyperparameters, our ability to improve our algorithms in an objective way is kind of challenging. So we have to find new approaches based on refuting assumptions, running sensitivity analyses, and then when we can, validating based on experimental methods, although that's so far not a approach we can use broadly. If we have the ability to run experiments all the time, then we actually would prefer to do that directly. The second challenge we face is really that we need to bring in this domain knowledge. And in our experience, we're finding that the approach that we usually take of asking an expert to provide us that domain knowledge isn't reliable. It's difficult to find a domain expert who understands the system well enough to very succinctly and clearly enumerate the potential causal relationships that we need to know about to guide our causal ML algorithms. And when we don't have the even when we do have that domain expert who understands the system well enough to give us that guidance, it's often the case that they aren't an expert in causal learning, which means that they have a difficult time expressing their knowledge in the form of a causal graph. This means that that really we need to often bring together a team of people to work together. And this is not always feasible. There simply aren't enough experts. There isn't enough people who understand causal learning well enough, and it's too easy to make a mistake. So we are researching new ways to elicit domain knowledge from people, looking at, for example, human-computer interface methods and others. We're looking at new sources of domain knowledge, for example, simulators that already encode many of the causal mechanisms in many domains, and also looking at other sources of domain knowledge as well, such as more vertical, domain-specific tools that maybe aren't general purpose, but are very valuable for broad sets of scenarios. The third challenge we face is kind of understanding that the audience of real-world decision makers is actually much broader than data scientists who code. This means that we have to find ways of making these methods accessible not only to data scientists who know Python or R or MATLAB, but also to decision makers or decision drivers who are more comfortable with data dashboards or Excel or other types of formats. So how do we make these methods, this whole process of causal decision making, accessible via interfaces that don't require coding? And finally, in many of the exciting applications where we want to be making decisions, whether it's healthcare or agriculture and its reliance on satellite imagery, the evidence, the data that we have to describe a particular situation is not tabular. It's not easily described by a list of variables. We have to support more unstructured and very high dimensional data sets. And this is not something that causal inference algorithms have done in the past. So we're developing new causal deep learning methods to model text and images and other data types. In the rest of this talk, I'm going to dive a little bit into some of the approaches we're creating to validation and how we're supporting unstructured and high dimensional data. So without data-driven cross-validation, what can we do? I mentioned that DoI is built around a process that brings assumptions front and center. And these are the 4 key steps of causal inference editing codes. First, we ask the user to model their system and create this causal graph that encodes their understanding of the mechanisms, the patterns that we want to learn from, and implicitly the ones then that we want to ignore. Then we analyze and reason over this model to identify a strategy of how to estimate the answer to a question we care about. Then we have statistical estimation methods that will compute that estimate. And finally, we'll double check all of our assumptions, both those implied. We'll double check all of our assumptions and see if any of them might be wrong. And in cases where we can't directly validate an assumption, we'll see if we can refute it instead, or if we can run sensitivity analyses that tell us how wrong we'd be if the assumption is broken. Some of the assumptions, just to give you a sense of the kinds of assumptions that we have to be concerned about, these assumptions can be implicit in all of these steps. So when we're modeling, asking the data scientist to model the system, we have to be aware that maybe the expert missed some variables in the assumed graph. Maybe there's parts of the system that are important but are not being observed. What happens if we forget one of those? What happens if there's a potential relationship between 2 variables in the graph that aren't encoded? We think that 2 things are independent when really they're related to each other. When we're trying to find a strategy for estimating an answer to a question, often these methods make some sorts of parametric assumptions, maybe a monotonicity assumption, for example, that says that we assume that some value only increases another but never decreases it. And of course, our estimation methods themselves often assume functional forms. They might assume a linear relationships or make other kinds of assumptions when they're trying to learn the relationship between 2 variables. Sometimes these estimator assumptions might lead to high variance. How do we validate these? So the best practice, given that we can't do a cross-validation or other kind of comparison to ground truth, is to do a refutation or robustness tests for as many of these assumptions as possible. And in DoI, we've encoded a number of these. We validate the model through conditional independence tests. That is, we make sure that the causal graph that a user has given us is consistent with the data we are analyzing. We will run end-to-end tests as well that, for example, add in additional data, fake treatments or dummy outcomes, and validate that end-to-end we don't get surprising results. If we pretend to give people a randomized placebo by adding a dummy column to our data set, we're pretty sure that that dummy placebo shouldn't have any effect on an outcome that we observed in real life. And if we do, that means that there's, for example, a coding bug in the system or some other kind of significant error. In other cases, we can run sensitivity analyses as well. For example, we will add in an engineered fake treatment or a fake confounder that accounts for some of the correlation between a treatment variable and an outcome. And now, as we change the strength of that confounding variable, we can test to see how closely, how significant that confounding variable has to be. So let me go through some of the details of these. For example, if we have a particular causal graph, this causal graph implies conditional independence constraints on its node. So for example, we see that A is independent of B. There's no arrow or path that connects A to B or vice versa. This means that if we look at the data at the values of A and we look at the values of B, they shouldn't be predictive of one another, they should be statistically independent. And we can test, use an appropriate statistical test of independence. And if it fails, that means that this model, this graph, is incorrect. And we can do this for every other conditional independence in this graph too. For example, A and T, if we condition on W, if we block the influence of A on T through W, then A and T should be, any variance in A and T while keeping W constant should be independent as well. There shouldn't be an influence of A and T if W hasn't changed. Same thing for the influence of B on T. And if any of these conditional independence tests fail, then we would warn the user and ask them to double check their understanding of the system before continuing. The placebo treatment I mentioned, we would generate a data set where the treatment does not cause the outcome. Say we will replace the original treatment variable here with a placebo that we know is completely independent of everything. Then we run our analysis, and if we find that there is a non-zero effect of T on Y, then our analysis procedure is incorrect. In other cases, we can add a new unobserved confounder. And as we change the strength of this unobserved confounder that is correlated with both T and Y, we can see how that affects our analysis. How significant does the size or the correlation of U between T and Y have to be before the effect of T and Y flips, for example. Now, these sensitivity analyses, these refutations are not affirmative validations of an analysis, but they can tell us when things might be wrong. And in practice, we find that they often can help us a priori identify the best models, even when the assumptions aren't theoretically verifiable. So in one study that we applied to data from our Office applications, we wanted to identify a particular causal effect, and we were able to, we found that the models that were performing best in our sensitivity analyses, the ones that were least influenced by the addition of, say, a confounding variable, a fake confounding variable, those were also the models that did the best when we validated these analyses with a randomized experiment. And that gives us hope that when we run these analyses in a real world, when we don't have the opportunity to run a randomized experiment, that they do actually give us some, at least empirically, some a better likelihood of getting the right result. Similarly, the results that did the worst in our sensitive analyses also did the worst in our randomized experiment. So to recap, our causal methods rely on causal assumptions that come out from a source outside of the data itself. They come from a human expressing their domain knowledge in some form. And validating our result depends on trusting these assumptions. So it's critical that we do everything we can to ensure that those assumptions are correct. We can run a number of automated tests like refutations and sensitivity analyses, but as of yet, there is no silver bullet to be sure that our causal analysis is correct, and that improving this situation remains future work, very important future work. The second challenge that I wanted to dive into is the challenge of extending causal inference methods to support unstructured and high dimensional data. Can we apply causal machine learning to images and text, especially given how much information is currently captured as image and text in many of the applications that we care about? So causal analysis, it doesn't currently handle such high dimensional data very well. even though this high dimensional data is useful for many scenarios, whether it's online computing systems such as ads or recommender systems, whether it's health scenarios, which rely on electronic health records, including their text notes, clinical notes encoded in text, or medical images from CT scans or MRI scans, or other kinds of industry scenarios that rely on satellite imagery, drone photography, etc., for informing, say, forestry management, agriculture management, methane leak detection, etc. We've published a couple of papers on archive applying to that are developing new methods for images and for text. I'm going to dive into this first paper, which is improving the robustness of causal representation learning approaches for images. Now, to set the stage a little bit for this algorithm and connect it to our challenges of causal inference, one of the challenges when we're looking at images is that there are a lot of potential signals in the image, but none of the raw data, the pixels that we have, individually correspond to the different elements of the causal graph, the semantic knowledge we have about a system. So what we want to do is, what we'd like to do is identify the information in that image, just the higher level representation of that image that is relevant to a particular causal graph, to a particular causal task that we are trying to address. So if you think about the causal graph in our node that represented irrigation, maybe we have a picture of a field from the past and we want to tell from the picture whether the field has been irrigated or is being irrigated right now in the picture. Now, converting that image and the information in it into our semantic feature that we care to capture is challenging, but it's related to the task of representation learning. How do we convert from that image into a particular label or kind of a feature that we want to extract, while avoiding being confused by other information in that image. Now, one area where people have been working on this problem is in the context of image classification and domain generalization algorithms. But domain generalization algorithms, it turns out, don't have a hard time generalizing across different kinds of distribution shifts. So Wiles et al. At ICLR this year, they showed that the different kinds of domain generalization algorithms did not do equally well when when a data set was perturbed with different kinds of data shifts. When you added spurious correlation, some sort of unseen data shift, or a sampling related issues in particular scenarios, they found that different algorithms did better. And in general, this is generally true. The best methods for domain generalization are not consistent across different data sets and shifts. Moreover, they all have problems when different kinds of distribution shifts are happening simultaneously. So we might, for example, find that satellite imagery data sets are shifting both in time and in location in different ways simultaneously. Now, what is the causal perspective then on this problem, and how can we improve the domain generalization so that we can apply so we can apply representation learning in the to pull out the causally relevant features that we can then use in downstream causal machine learning tasks. Well, when we looked at the different kinds of distribution shifts that people were experimenting with, we realized that we could think of these distribution shifts from a causal perspective. And we could identify that the times when domain generalization algorithms did better or worse could be tied to the kind of causal mechanism that was changing as you went from one distribution to a different distribution. That is, in a sense, I guess I'll say that these algorithms each assumed a specific kind of distribution shift that corresponded to a particular causal mechanism. And as long as the distribution shift could be represented with a particular causal mechanism, that algorithm would do well. But if you had a very different kind of causal mechanism, a different relationship that was generating your distribution shift, that algorithm would do poorly. And of course, different algorithms are encoding different kinds of constraints, different assumptions. And that meant that none of them worked well really across all shifts. So our solution then is to explicitly model the kind of causal relationship and then analyze the kind of relationship to identify the specific constraints we would want to impose during learning. So here is the stylized causal graph we use to encode different kinds of attribution shifts. So here I'll go through these slowly. We have some object that we're trying to capture. We have a image, a high-dimensional image X, and we have some label Y. So this is maybe an outcome that we care about. So maybe this is the whether or not we're irrigating is Y. We see the signs of irrigation. The true irrigation, whether we're irrigating or not is this object, and the signs of that irrigation that's then being shown in the image and influencing our ground truth label are captured in X sub C. And then we know that the image is also independently being influenced by a number of other attributes: the season, the crops, where in the world you are, etc. Some of those you might think of as being correlated with a specific environment. And of course, sometimes the environment or these attributes might be correlated with the existence of this object as well through some mechanism. Now, it turns out that if we want to, what we're trying to do is disentangle the parts of this high-dimensional data, this high-dimensional image X. We're trying to disentangle that into the parts that are being caused by this X sub C that we're trying to learn a representation of, and ignore the parts that are caused by these other attributes A that we really want to ignore. Of course, because they're all correlated with each other, they're correlated with Y, maybe they're correlated through the environment as well. It's not trivial to disentangle these things. What our algorithm does is it pays special attention to the relationship between this label Y and these other attributes. And if they are correlated with each other because of, say, selection bias, because of a confounding relationship, there's some other unobserved variable that's causing both Y and this attribute A, or there's some direct relationship, maybe Y is actually causing A. Based on what kind of relationship we believe exists between Y and A, we're going to impose a different kind of constraint when we go and try to learn X sub C. This method of analyzing this relationship between Y and A and using that to determine the constraint that we're going to assert in our learning, we call causally adaptive constraint minimization. And in our experiments, we find that it significantly improves over existing algorithms when we cause distribution shifts of different kinds. And it continues to work well when we have multiple attributes shifting. This table here shows experiments that we ran on an MNIST data set where we both used colored MNIST and then a rotated MNIST and a colored and rotated MNIST, where we controlled the kind of causal relationship that was generating the color and rotation and the label, and shifted them differently. In this particular case, we applied the constraints implied by the underlying causal relationship as a regularizer to ERM to obtain the suitable loss function. So whereas some methods like IRM always assert the same constraint on the loss function, we would adapt that based on the causal graph. So the first phase of our algorithm is to derive the correct independence constraints. Here we look at all of the observed variables in the graph and check to see whether or not the variable, the x sub c and a, the particular attribute a, is deseparated or independent. If it is, then we add a constraint that forces x sub c to be completely independent of a. That means that a and our learned representation must be independent. If they are not deseparated, then we'll check to see whether x sub c and a are deseparated when we condition on any particular subset of the remaining variables. And if so, then we can impose that constraint instead. Finally, given these constraints, we put them together and apply a regularization penalty derived from those constraints. We use an MMD constraint there. The final regularization penalty is a sum of the penalties over all of these attributes. And we apply these by adding the penalty to the standard ERM loss. We provide a complete theorem of this in our paper, which includes the derivations for the constraints for these four kinds of shifts, as well as general graphs. We find that in our experiments on colored MNIST and also in a data set called small norb, which is a photo data set of small toys taken under different lighting conditions and different angles, that our algorithm provides an up to 20% improvement over other algorithms. So the takeaway here is that understanding the causal relationships that are causing the spurious patterns, these correlations between these attributes A and the information we want to extract out of the image is critical to ensuring that we learn that representation correctly. It's necessary to model those causal relationships in the data generating process to succeed at causal representation learning and domain generalization. And this causal representation learning then is a key part of disentangling this high dimensional data to find specifically what is relevant for causal task. So once we have identified a representation of that x sub c, ignoring all the other irrelevant attributes, then we can now use this x sub c in other tasks that rely on that and use it for effect inference or other kinds of causal tasks. This now I've spoken about broadly about causal machine learning and why it's important for decision-making applications. I've reviewed kind of based on our experiences with applying causal machine learning through our open source tools and our first-party applications. I've discussed some of the challenges we see in using these methods in practice. And I've discussed some of the approaches we're taking to create processes for validating causal methods when we can't do cross-validation, given that we can't do cross-validation. And I've also dove into some of the ways that we're thinking about new methods that connect causal machine learning methods with models of unstructured or high-dimensional data, such as text and images. This brings me to the end of my talk today, and thank you very much for listening. I'd be happy to take questions.